Good afternoon. My name is Sahil Trivedi, and this is my public lecture review on quantum tunneling. So, I attended the lecture where we discussed quantum tunneling in depth, and it was what the Nobel Prize award was given to in the past. And the main idea of this lecture was really just explaining how quantum tunneling works and what it actually means in terms of observing things um, that are not actually, would not be happening according to the macroscopic view of physics, but on the quantum level could in fact happen just due to quantum interactions as well as some level of um, probability. Now, looking at this lecture, the main thing that I found that was very, very interesting was the fact that things that could be completely in conflict with the macroscopic view of um, physics and the way we accept it are possible on the quantum level. Something as simple as it's even possible to stick your hand through a wall or um, something of that nature if it were done an infinite amount of times due to interactions at the quantum level. And that was one of the main points of the lecture, and what I have pulled up here in the video that you can see. So here's this activation energy, and although the object just has 9 sort of units of energy and the activation energy is 10, sometimes it can tunnel its way through the barrier, and this can reach a lower energy state. I found this to be very interesting. If we keep scrolling down, you can see some of the math here. I found this to be very interesting because this essentially expedites the race to an energy level that is 0. We all know that the universe, is always trying to become more and more stable and reach a lower energy state. And given enough time, things like quantum tunneling allow us to reach lower energy states when we even think that they're not possible, just from a complete violation of activation energy for certain reactions. Now, something very interesting that I wanted to follow up with, and an idea or concept that was not discussed fully in depth by the lecture, was the idea that, given an infinite time horizon, there's kind of 2 areas of debate. Does everything just fuse into the most stable element due to gravitational pull over time, which is iron 56, or does quantum tunneling allow us to, go even lower than that and see some sort of violation of activation energies, and see protons decay and things like that? If protons don't decay, then I assume everything will reach that iron 56. But if protons do decay, then we can reach even lower and lower energy states. Now, continuing on through this, it's a lot of dense math, which was, obviously very, very hard to follow. But going on, you can even see kind of the experiments and everything that they do here. And I saw that this related very well to what was discussed in the guest lecture, in talking about sort of, how do you actually measure quantum tunneling? How did we discover quantum tunneling? And I think that actually understanding it, if quantum tunneling was true and we had an infinite time horizon, technically the universe should just go completely dormant as we will reach energy states which we didn't think were possible, just as the universe is trying to become more stable and more stable. I think this is something that the guest speaker could have touched on a little bit more, or if I had the time to talk to him further, it would have been quite interesting. But I did find his overall sort of presentation very, very interesting, and I think it's something that a lot of people have not had familiarity with. I've seen it a little bit in some science videos and things of that nature before, but yeah, essentially it didn't. The sort of proton decay and transformation to iron 56 is just something I wanted to know kind of more in depth. Overall, I thought it was very insightful, and I'm glad it happened. And I would recommend anybody go to one of these guest lectures if it was anything like this one on quantum tunneling. Thank you.